What happens when a really massive star runs out of fuel? And how are the elements of life created? What is a supernova? And should we break open the champagne if we see one? How are neutron stars and black holes formed? And what have neutrinos got to do with it all? I'm Nicholas Mee, welcome to the Cosmic Mystery Tour. In the previous video, we looked at the fate of the Sun. We will now turn to much more massive stars that end their lives not in a whimper, but in a very big bang. Stars produce their energy by converting hydrogen into helium in their core. And when the hydrogen runs out, the core contracts, the temperature rises, and a new round of fusion reaction begins. The helium is converted into carbon and oxygen, and meanwhile the star inflates to form a red giant. Because red giant stars are so enormous, they are much more luminous than the Sun. One of the most famous examples is Betelgeuse, which is the fiery red star that forms the shoulder of Orion the Hunter, a prominent constellation in the Northern Hemisphere winter night skies. Betelgeuse is so large that if it was placed at the centre of the solar system, it would swallow up Mercury, Venus, the Earth, Mars, the asteroid belt, and extend out to the orbit of Jupiter. It's estimated to be about 100,000 times as luminous as the Sun, and it's so vast that we've even managed to produce an image of its face, which we can see here. Even at a distance of 640 light years, Betelgeuse is one of the brightest stars in the night sky. Antares is another spectacular red giant star. It's in the constellation Scorpius the Scorpion, which is visible in summer night skies. Antares gets its name from its blood-red colour, which rivals that of the planet Mars, or Ares in Greek. Antares has about 15 times the mass of the Sun, and it's inflated almost as large as Betelgeuse. So even at a distance of 550 light years, it's one of the brightest stars in the night sky. In a really massive red giant star, the nuclear fusion processes in the core go through several phases. Each is at a higher temperature than the last, and each lasts for a shorter period of time. Helium is converted into carbon and oxygen. Then when the helium fuel runs out, the core contracts and the temperature rises to hundreds of millions of degrees. And this triggers fusion of carbon to form oxygen, neon and magnesium. Then in the next phase, sulfur and silicon. And finally, iron and nickel nuclei are formed, and by now the temperature in the core has reached billions of degrees. Iron is the densest of all atomic nuclei, so no further energy can be generated by fusion with iron. So at this point, the core of the star collapses, and this triggers a supernova explosion in which the star tears itself apart. A supernova is as bright as an entire galaxy. That's 100 billion times as bright as the Sun. Much of the light that we see from a supernova explosion derives from the radioactive decay of nuclei of nickel and cobalt to form iron nuclei. The light from the supernova decays over a period of several months, and this period of time is determined by the half-life of these isotopes. The elements of life, carbon, oxygen, sulfur, silicon, magnesium and iron, are dispersed throughout the galaxy in supernova explosions. The debris from these explosions merges with the gas clouds that go on to form subsequent generations of stars. So if it were not for the supernova explosions that occurred before the birth of the Sun and solar system, then we would not be here. Astrophysicists have made models of supernova explosions. but the precise mechanism that produces the blast is still not known with certainty. However, an elusive particle known as the neutrino certainly has a critical role to play. Neutrinos only interact via the weak force, and their interactions are so weak that a neutrino could pass all the way to the nearest stars through lead without an interaction occurring. The universe is full of neutrinos. The Sun produces them in vast quantities. Neutrinos are continually passing through us all of the time. When the core of a star undergoes its terminal collapse, the temperature and density at the centre of the star rise so high that protons and electrons interact via the weak force and are converted into neutrons and neutrinos. So the centre of the star becomes a mass of neutrons and a vast quantity of neutrinos are emitted. 99% of these just pass through the star and disappear off into space. But the other 1% smash into the collapsing envelope of the star, and this is what produces the blast of the supernova explosion. So what is left when the smoke clears? The collapsed core of the star has been compressed into a neutron star. This is a rapidly spinning body with about 1.5 to 2.5 times the mass of the Sun, squeezed into a sphere just 20 miles or 30 kilometres in diameter, with the density of an atomic nucleus. In the video Cosmic Butterflies, we discussed the mass of a teaspoonful of white dwarf material, which if brought back to Earth would weigh about 10 tonnes. But a teaspoonful of neutron star material would weigh 1 billion tonnes.